Focus on the lesson. Thank you. Let's talk about gravity. Objects in free fall on Earth accelerate at 9.8 meters per second squared. I've taught you that. We've verified it experimentally. Well, sort of. We dropped some objects from the back stairwell in Physics 11, and we tried to see using stopwatches if we could get the negative 9.8. And we could get close, but if we had a vacuum and good instrumentation, we could measure that 9.8 meters per second squared. Why do objects accelerate in free fall at 9.8 meters per second squared? Here's a phrase you want to underline: gravitational field strength. I'm going to start to use that phrase more and more often, because now we're going to start to think about free fall in terms of not being speeding up, accelerating, but in terms of gravity force acting on you, accelerating. The Earth has a gravitational field strength of 9.8 newtons per kilogram. Chantel, what do I measure in newtons? If I get an answer in newtons, what is that? What do I measure in kilograms? What is F divided by M? F equals what? Get that? Another way to write acceleration, yes, meters per second squared, and that's when we're talking about a change in speed, we'll think about it that way. But in this unit, more and more, we're also going to be talking about an unbalanced force. An acceleration can be thought of as newtons per kilogram. Earth has a gravitational field strength of 9.8 newtons per kilogram. Other celestial bodies have different gravitational field strengths. But the reason an object free falls at 9.8 meters per second squared is because Earth is tugging on every kilogram of that object with 9.8 newtons of force. There are two ways to get that 9.8. The first one is the one we did last year in Physics 11. You can drop an object in a vacuum and time its free fall. We did it in the stairwell using mg F net equals ma, solve for a by using Vf and Vi. The second way, by the way, is to use the force equation, because F equals ma. That means that F weight is mg. If I take a scale that I know is calibrated for newtons, here is a Newton scale, and I hang a known mass on it. This is a 1 kilogram mass. If I hang this on a Newton scale, how many newtons of force will the Earth exert on a 1 kilogram mass? Do the math in your head. Yeah, it's going to be really close to 10. Well, reverse that. If I know this is in newtons and I know what mass I have, I could go this divided by the mass, and that would give me Earth's gravitational field strength. Or if I could magically beam myself to the moon and do this experiment, I wouldn't see 9.8, I would see 1.6. I would say, oh, the gravitational field strength of the moon is 1.6. The problem with both of these methods, dropping an object and timing it, or using a Newton scale, is you have to be on the planet to measure its gravitational field strength. How do we figure out the gravitational field strength of places we haven't been yet? We had to know what it was on the moon before we built a system to land on the moon. We had to know what Mars's gravitational field strength was before we could send probes there. This was the question that Isaac Newton asked himself. Bring this back. This was the question that Isaac Newton asked himself. First of all, Caden, another way to say acceleration due to gravity is, what three words did I underline at the top of the page? Gravitational field strength, measured in, yes, meters per second squared, but what was the other units I said we could think about it as? Newtons per kilogram. Boy, that's a messy K. Okay. This is little g. 9.8 on the Earth. Newton wanted to figure out, how can we figure out the gravitational field strength, little g, on the moon, on Mars, on other celestial bodies? Can't go there. How can we figure that out? So Isaac Newton found that universal gravitational field strength. Finding the gravitational field strength, hey, near a black hole, anywhere in the universe, depended on two things. It depended on the mass of the planet or the star or the asteroid or the moon creating the gravitational field. And it depended on the square of the distance from the center of the planet. Now, most planets are spherical. What do you call the distance from the center of the sphere to the edge of the sphere? It's the radius. There's going to be an r again in our equations. In fact, it's going to be an r squared in our equations. Newton found this. If you want to find the gravitational field strength anywhere in the universe, little g, it's proportional to, I showed you that symbol a couple of units ago. That's an abbreviation for depends on or is proportional to the mass of the planet. He used a capital M to show it's the big object that's creating the gravitational field, divided by r squared. What were the units for little g? Gravitational field strength, meters per second squared. But what were the other ones I also said? Newtons per kilogram. What are the units for mass? What are the units for radius? This is kilogram per meter squared, which is not the same as newtons per kilogram. So to make the units work, you're going to need to put a conversion factor. This is what Isaac Newton discovered. He said little g equals, his conversion factor, he used a capital G. He called it the universal gravitational constant. Big M over r squared. That will give you an answer in newtons per kilogram. What is big G? It's on the back of your formula sheet. Go find it. I know it's up there too, but I need you to find it on your formula sheet so you know where it is, so that when you need it, you know where it is. You don't look at me blankly like, isn't it 9.8? No, little g on the Earth is 9.8. Big G anywhere in the universe, Anderson, what is it? Ten to the what? 10 to the negative 11? That's small. That's 0.0000000000667. It's crazy small. In fact, notice I wrote here how small g is, big G. By the way, I'll call this one big G. I'll call this one little g. Big G, you'll probably end up memorizing it during this unit at 6.67 times 10 to the negative 11. It's not a convenient number, Presley, but the universe doesn't have to be pretty and convenient for us. You'll get tired of typing it in, but you'll be typing it in an awful lot in almost every equation in this unit. It'll be there. Okay. That negative 11, gravity is by far the smallest of the four fundamental forces in the universe. Compared to electromagnetism, for example, it's 10 to the 20th times smaller. Electromagnetism is a 100 million times stronger than gravity. You think of gravity as being strong because it's the one that dominates your life the most, Caden, but it's a very weak force. Very weak. Now, Newton predicted the need for this big G, 6.67 times 10 to the negative 11, but he couldn't come up with an experiment to measure it. So he set all of his equations up so that the big G's would cancel. It took nearly 100 years before Henry Cavendish was able to measure big G. He did it in 1798. We call this the Cavendish experiment. It was a very, very clever experiment. Put your pencils down, look up. And he was within 10% of our current value, so he did pretty good. I have this muted because the music is both cheesy and I'll probably get a YouTube takedown notice if I play it. So here was his setup. He took a bar, he suspended it from some strings, and he put a couple of masses on the end of the bar. And the key idea was this beam, this bar, was free to rotate. So bar is suspended by fishing line. I apologize, this was made in 1996, so it's not HD or anything like that, but this is about the shortest, more concise version that gets you the idea. So he did this in an isolated room, Cavendish did. Let it sit, made sure it was all nulled out, let it sit for a few weeks. Key idea, the bar is free to rotate. Then what he did is he put a large mass right there and a large mass right there. This mass will gravitationally attract this mass. This mass will gravitationally attract this mass. And Jacob, what will happen ever so slowly, here's a time lapse, is the bar will ever so slowly start to rotate. This is sped up a bunch. From that rotation, he knew the force of the twist of the rope required to do that rotation, and he was able to come up with an equation and get big G by itself. Very clever. Really, really, really finicky. In fact, I'm not convinced that what we're seeing here is actually gravity. I suspect there's wind currents and other things here going on, but this gives you the gist of it, Presley. If I wanted to find a pristine version, this would probably need to be done in a vacuum if we wanted to do it bang on. But you can see again, when we switch the masses ever so slowly, time lapse, gravity pulls this mass towards this mass. By calculating, put your phone away, Tony, by calculating by measuring the torsion twist and using that to figure out how big the force of gravity had to be, he got the big G by itself. And he found the 6.11 times 10 to the negative 11. First thing he did, once we knew the value of big G, we could finally calculate the mass of the Earth. Up until then, the mass of the Earth had been a best guess. Literally what they had done is they had taken the mass of shovels of the Earth, averaged them out to get the mass of an average shovel of dirt, and multiplied that by the volume of the Earth. And that was their estimate for the mass. Cavendish did this. He said, okay, little g equals big G, big M over r squared. Newton's equation. He got big M by itself. Gibson, how would you get the big M by itself? How will you move the big G down? How will you move the r squared over? And little g, he knew 9.8. They had that back then, so he knew that. He said, okay, the mass of the Earth is going to be little g times r squared divided by big M. Little g is 9.8. We've known the radius of the Earth for about 2,000 years. It's on your formula sheet on the back page. Gibson, what's the radius of the Earth? Don't forget the squared. Divided by, and what did I put, what did I do dumb and wrong, Mr. Dueck here? I don't want big M there. I want big G there. I'm sorry, folks. We're getting the big M by itself. We're going to put the big G there, which is, what was it? 6.67 times 10 to the negative 11. All of you want to practice typing this in because the calculations in this unit are going to be that scientific notation-y or worse. So you want to make sure you know how to use your scientific notation button with squares and fractions and whatnot. And if you do it right, because I know the mass of the Earth, you should get 5.98 times 10 to the 24th once you type this in. Once you type this in. All of you should practice typing this in on your calculator because this is the level of scientific notation-iness you're going to have to deal with. Thanks for getting the hint the second time. Do you get 5.98 times 10 to the 24th? Which I think is what the mass of the Earth is on your formula sheet as well, yes? Cavendish sat there with that number. First of all, delighted because he was the first human being to actually know the mass of the planet that we are on. But he also went, that is way too big. based on the value that he had. This was the first hint that it's not dirt all the way down. They had assumed up until then that it was dirt all the way down. What do we think now is at the center of our Earth? That's dirt. And not at the very center. What do we think is at the very center? Anybody know? Done a little geology or geography. So we believe the center of the Earth has a very dense molten iron core. We think the heavy metals over eons, over billions of years, have sunk down to the very center. And that's denser, heavier per volume, than just dirt. That's why Earth's mass is more than just dirt all the way down. And that allows us to explain Earth's magnetic fields. We think that that iron core it's in a weird state, solid, liquid, gas, plasma. Those are the big four. It's under pressure. It's in a weird, obscure state of matter. I don't even remember the name of it, but it neither fits into a solid, liquid mass or plasma. But among other things, we think it's spinning. In fact, we think there might be an inner core and an outer core, and we think that interaction is what gives Earth its magnetic field, which is good. Otherwise, we'd all be dead. The reason Mars has no water, we're pretty sure had a lot of water once. Mars never had a magnetic field, and so the sun's solar wind, particles from the sun streaming at it over billions of years, just eventually lifted the water away. Most of the sun's particles that hit the Earth are deflected by the Earth's magnetic field. That's what we call the aurora borealis and the northern and southern lights. Okay. So what's little g on the Earth? 9.8. On the moon, heavier or lighter? Is g bigger or smaller? Yeah, this is actually kind of nice. NASA put this together. Here is a 1 kilometer drop on a bunch of different astronomical solar bodies, and it's to scale. So look up, watch for a bit, put your pencil down. Thank you. We have everything from the sun. Little g on the sun is 274. G on Mercury, 3.7. Here's good old Earth, 9.8. If we drop an object 1 kilometer, that's how long it would take to fall a kilometer on the sun. Jupiter has the next strongest gravitational field. You can see Venus, Earth, Saturn, Uranus, and Neptune all relatively close to each other. Which two are the smallest? What Ceres? It's actually the largest asteroid in the asteroid belt. And in fact, it was one of the reasons we had to demote Pluto. We were either stuck with, as telescopes got better and better, we had found 4 other roughly Pluto-sized objects, and it was going to be, are we going to go up to 13? Or are we going to actually define what a planet is? So what we did instead is we defined what a planet is. I'm going to stop. I'm not going to wait for the whole fall. I'm going to hit pause now, though.